Welcome to our next lecture in Chapter 4, 4.3, Diagnostics on the Least Squares Regression Model. In Section 4.2, we discussed how to find the least squares regression line using formulas and technology. Here we're going to present additional characteristics of the least squares regression line, along with graphical diagnosis tests to perform on those lines. We're going to look at computing and interpreting the coefficient of determination. We're going to perform residual analysis on a regression model and identify influential observations. First objective is to compute and interpret the coefficient of determination. The coefficient of determination, labeled uppercase R squared, measures the proportion of the total variation in the response variable that is explained by the least squares regression line. The coefficient of determination is a number between 0 and 1 inclusive. That is, 0 is less than or equal to uppercase R squared, which is less than or equal to 1. If R squared equals 0, the line has no explanatory value. If R squared equals 1, the line explains 100% of the variation in the response variable. Deviation. The deviation between the observed and mean values of the response variable is called the total deviation. So total deviation equals y, which is an observed variable, minus the mean of the y, or the response variable. The deviation between the predicted and mean values of the response variable is called the explained definition. So the explained definition equals the y hat line regression value, or the predicted value, minus the mean of the y variable, or the response variable. The deviation between the observed and predicted values of the response variable is called the unexplained deviation, which equals y, which represents every observed value of the response variable, and minus y hat, which is the linear regression line that we done to predict values. In the figure shown, a horizontal line is drawn at y equals 266.75, and you can see this is the average value of all of them. This is the average value of the response variable, or the mean of the response variable. Or we can think of this as the predicted distance of a shot without any knowledge of the club head speed. Now, what do we mean by that? Well, if we don't know what the speed the club is going at, we don't have any real connected data points about where on this graph we are, so we use the average value of all of the shots. So if we don't know the speed of the club, then we just use the average value of all the observations, and that's what we're talking about here. You can see that we have a difference, a deviation explained by the club head's, unexplained by the club head speed, and a difference or deviation explained by the club head speed. And this is what we were talking about in the prior graphic, and we'll go into a little bit more detail now. If we know that the club head speed is 103 miles per hour, we increase our guess beyond the mean to 270.3. The difference between the predicted distance for all means of 266 and the predicted distance of 270.3 is due to the fact that the club head speed is 103 miles per hour. So we have some data that we're inputting here, and so what we're doing is we're using the linear regression line prediction versus just the average. In other words, the difference between the prediction of y hat, or the linear regression, 270.3, and the mean of y, 266.7, is explained by the linear relation between club head speed and distance. The observed distance when the club head speed is 103 miles per hour is 274 yards. The difference between our predicted value, y hat, and the actual value, y equals 274, is due to factors or variables other than the club head speed. It might be wind speed, it might be position of the ball and the club face, and so on, and also to potentially random error. These differences just discussed are called deviations that we saw on a previous slide. So the explained deviation is y hat minus the mean of y, where the unexplained deviation is the observed value of y minus y hat. So let's look at the how the coefficient of determination and variation are connected through a relationship between deviation and variation. So we've seen that total deviation equals unexplained deviation plus explained deviation, and we can see that in the formula here too. Total deviation equals unexplained deviation plus explained deviation, and we can see that the y hats are going to cancel out, leaving us the same thing on both sides of the equation. Remember variance from chapter 3 when we took the summation of, we took the standard deviation squared and added those all together, okay? So this is very similar to that, and you'll recognize these formulas look very similar to standard deviation formulas, again, from chapter 3. So the total variation, y minus the summation of y minus the mean of y squared for each member, equals the unexplained variation, y minus y hat squared and then added up for each observation, plus the explained variation, which is y hat minus the mean of y squared, summed up as well. Okay, so we're going to do a little algebra here, and notice if we divide each term by total variation, which is what's on the left side of our equal sign here, we get 1 equals unexplained variation over the total variation plus the explained variation over the total variation. Again, here's the total variation. Okay? Well, remember that, maybe not remember, but the coefficient of determination, or r squared, is equal to the explained variation over the total variation. R squared, the coefficient of determination, is equal to explained variation over total variation. So this equals 1 minus the unexplained variation over the total variation, right? So all we've done here is subtract the unexplained variation over total variation from both sides, and so we get a formula here for the coefficient of determination. So notice that we're looking at how to find the coefficient of determination, uppercase R squared, specifically for the least squares regression model, where y hat equals b1x plus b sub 0. That is, we're looking for a single explanatory variable to the first degree. All that's saying is that this is a linear equation as long as the exponent on the linear variable x, the explanatory variable x, is a 1. Okay, that's the first degree. All we have to do, if we have this situation where we have the least squares regression model, we can square the linear correlation coefficient. That is saying that the coefficient of determination, uppercase R squared, is equal to the square of the linear correlation coefficient, which is lowercase r squared that we saw in chapter 3. Be careful though, the squaring the linear correlation coefficient to obtain the coefficient of determination works only for the least squares linear regression model. And in general, this method doesn't work. Let's look at an example. To reinforce the concept of the coefficient of determination, let's consider 3 data sets. We have data set A here in the first 2 columns, data set B, and then data set C. One of the things I want you to notice is that the y values, 8.9 to 13, are the same in all 3 cases. This is just helpful to make our calculations and comparisons a little more easy. The other thing I want to remind you is that most of the examples, like here, this table 7, are available to preload into StatCrunch, meaning you don't have to retype all this data, and if you want to practice with StatCrunch, you can do so via the MyLab Statistics StatCrunch link. This is in eCampus, and it's on the MyLab Math page in eCampus. If you page down, you'll see a link that says MyLab Statistics StatCrunch. If you go in there, it has data sets, and typically, like I went to find this one, and what I did is when I went to the grouping of data sets, and there's thousands in there, I just wrote coefficient of determination, and I think 2, maybe 3 data sets came up. I clicked on the first one, and it was this table. So I encourage you to be looking at those so that you can, you can get some practical experience with StatCrunch before you hit the test. So we have 3 data sets. The y values, as I just mentioned, were the same. So the variance on y is 17.9. And we can see the scatter plot here with the linear regression. The first one looks really linear, and we can see that the coefficient of determination is almost 100%. It's 99.99, okay? The second data set B, it's still pretty linear, though it has a little bit more of a variance. And you can see here that the coefficient of determination drops down to 94.7%, or just under 1.94. And then finally, the last data set C, you can see is all over the place. This really does not fit a linear model. And you can see that the coefficient of determination is really low. It's at 0.09 or 9.4%. Okay. Notice that as the explanatory ability of the line decreases, the coefficient of determination also decreases. Right? So as we move away from what looks like a relatively linear placement of observations, as we see here, then the coefficient of determination is decreased. So let's look at another example. Determine and interpret the coefficient of determination for the club head speed versus distance data shown in Table 5 that we used earlier. The figure shows the results from Excel, and the coefficient of determination is highlighted. Again, that table is in your StatCrunch, so you could also use StatCrunch for that. Now, what does this mean if the coefficient of determination is 0.88? Well, it means that 88% or 88.2% of the variation in distance is explained by the least squares regression line. Okay? And 11.8, the remaining percentage, the remaining portion of 100%, is not explained by that, or it's explained by other factors. Okay? It's the unexplained portion versus the explained portion. Explained by other factors means it's not explained by the explanatory variable. So this is a really good example of how we use this coefficient of determination. Our next objective is to perform residual analysis on a regression model. Residuals play an important part in determining the adequacy of the linear model. In fact, residuals can be used for the following purposes: to determine whether a linear model is appropriate to describe the relation between the predictor and response variables, to determine whether the variance of the residuals is constant, and also to check for outliers. To determine if a linear model is appropriate, we also need to draw a residual plot, which is a scatter diagram with the residuals, the calculated residuals on the vertical axis, and the explanatory variable on the horizontal axis. When we do that, if a plot of the residuals against the predictor variable shows a discernible pattern, such as a curve, then the response and predictor variables may not be linearly related, and we can't use that for insight and inference. So here we have two residual plots. Notice we have the residuals plotted on the y-axis versus the observations on the x-axis, and the same thing we have in the second graph. So based upon this, which of these graphs shows some kind of discernible pattern indicating that it's not linearly related? Well, the first diagram shows no pattern. It really literally is a scatter again. So a linear model is appropriate for this pattern, for this absence of pattern, for this data. On the second graph, we see it looks roughly like some kind of shape or curve that's going through here as x increases. So in this case, because there's a U-shaped pattern or a pattern at all, the linear model is inappropriate. So let's look at an example to determine if a linear model is appropriate. The data in Table 8 were collected by placing a temperature probe in a portable heater, removing the probe, and recording the temperatures in degrees Fahrenheit over time in seconds. Determine whether the relation between the temperature of the probe and time is linear. Hint: enter the data into statistical software or graphing calculator with advanced statistical features. Figure A shows a scatter diagram of the data from StatCrunch. And it does look like a linear model would be appropriate, a negative linear model, right? If we do the calculation for the linear correlation coefficient, lowercase r, this coefficient is negative 0.997, which is really close to -1, which is giving us an indication that a negative association exists between time and temperature, that as time goes up, temperature goes down. So it would seem, at least at this point, that a linear model would be appropriate. However, it's not always clear just by looking at the data here and the pattern in the data. This is where the residual plot can really come in handy, where we sometimes get almost like a false positive result from the data. Looking at the residual plot can tell us if a linear model is indeed in order. So figure B here shows a plot of the residuals versus the explanatory variable, time, using StatCrunch. Here we can see we have an upside down U pattern in the plot. And remember that if we see a pattern, then this indicates a linear model is not appropriate. In fact, the predicted values overestimate the temperature for early and late time and underestimate the temperature for the middle times. And so while it looked like we had a negative linear model, in truth, we do not have that linear model for this specific study. Is the variance of the residuals constant? If a plot of the residuals against the explanatory variable shows the spread of the residuals increasing, the distance between them is increasing or decreasing as the explanatory variable along the x-axis increases, then a strict requirement of the linear model is violated. This means it cannot be used, and this requirement is called the constant error variance. The figure below illustrates the idea behind constant error variance. In figure A on the left, the data appears more spread out as the explanatory variable along the x-axis is increasing, specifically with x values larger. You can see the data points here at the far right of graph A are getting further apart than they are when we first started. In the residual plot in figure B, the absolute value of the residuals is larger when x is larger and smaller when x is smaller. So again, we have this. This means that the predictions made using the regression equation will be less reliable when x is large because there's more variability in y. You can see here again that they are more spread out here versus the residuals close to x equals 1 or lower values. We looked at outliers before, and remember that an outlier can be thought of as an observation whose response variable is inconsistent with the overall pattern of the data. To determine outliers, either construct a plot of residuals against the explanatory variable or draw a box plot of the residuals. Outliers can be found using a residual plot because these residuals will lie far from the rest of the plot. Now let's look at an example. Identifying outliers. Figure A on the left shows what appears to be an outlier here in the middle on the top, and it is labeled. This is the scatter diagram in general, and we can see that this point seems to be away from this kind of grouping or conglomeration of data points. Figure B shows a residual plot, and we can see that there is an outlier here that's far away from the other values, the residual values that we see. And finally, figure C shows the box plot of the residuals, and we can again see that outlier out here around the residual value of 10. So we can see that the data do contain a outlier, and we labeled the outlier in each of the figures there. Now let's look at graphical residual analysis based upon the graphs that we've just seen in the previous examples. Here we have the data from table 6, which we saw before, representing the club head speed and using two different prior examples, I believe, in the last section. Here we have, again, the data in the table is the club head speed, the distance the golf ball traveled, the residuals in column 7 for 8 swings of a golf club. And here we want to construct a residual plot and a box plot of the residuals and comment on the appropriateness of the least squares regression model. Remember, if there is a pattern in the residual plot, then the least squares regression model is not appropriate. Figure A shows the residual plot here on the left, and figure B shows the box plot. I mean, it looks like a giant misshapen donut, which really means that there's no pattern here. There's no kind of pattern as x increases. It's not a curve up or a curve down, linear, etc. Since there's no discernible pattern in the residual plot, a linear model is appropriate. And the residuals display constant error variance here on the right, and so no outliers appear in the box plot of the residuals. And this kind of makes sense. Since there's no pattern, how can there be an outlier, right? An outlier is something that does not fit the pattern of the data. And if there's no pattern, then it's likely that there's not likely to be an outlier. Objective 3, identify influential observations. An influential observation is a study observation, that significantly affects the least squares regression line slope and or y-intercept, or the value of the correlation coefficient. So if the correlation coefficient, slope, or y-intercept changes significantly, the removed point is influential. Here we see a diagram of the scatter plot, of the explanatory variable and the response variable. Case 1 is an outlier because its y value is large relative to its x value, and it's not within the pattern that we see. Case 2 is large relative to both its x value and y value, but it kind of follows the overall pattern of an increase of the data. And case 3 is large relative to its x value, and its y value is not consistent with the pattern of the data, which is increasing, and now all of a sudden the y value for case 3 is much lower. Okay, so these are pieces that we want to observe in the original scatter plot. And how influential it is affected by two factors: the relative vertical position of the observation, these are the residuals, up and down, the y's, and the relative horizontal position of the observation, right? The observation as compared to means or etc. And the relative horizontal position, and this is a new term which we're calling leverage. When I was talking about means, I was referring back to the vertical position. Leverage is a measure that depends on how much the observation's value of the explanatory variable differs from the mean value of the explanatory variable. Okay, so again, what we're talking about here is the average of the x-axis. Where is the mean here, and how far are points away horizontally from that mean value along the x-axis? Okay, case 1 has low leverage. It's not far away from the mean value, but it has a large residual, which means it's relatively far away from the data in general, or the mean for the average for the y value or the response variable. Case 2 has high leverage, right? It's far away from the mean of the data, and a small residual, meaning that it looks like if we continued on, that the vertical position is kind of in line where we would expect this to be going. And case 3 has high leverage, that the horizontal position is far away, and large residual, meaning that it's also outside of what we'd expect vertically or from the mean here. And it's below it, but it's still far away. Observations of this type of case 3, observations specifically with high leverage and large residual, tend to be very influential in terms of our definition. So our last example is about identifying influential observations. Suppose that our golf ball experiment calls for 9 trials, not 8 like we had before, but the player that we are using hurts his wrist. Luckily, Justin Thomas is practicing on the same range and agrees to participate in our experiment. His club speed is 120 miles per hour and he hits the golf ball 305 yards. Is Justin's shot an influential observation? The least squares regression line without Justin is y hat equals 3.1661x minus 55.7966, as we've learned in prior examples. Here we have the data, including Justin's data, calculated using Minitab. The least squares regression line with Justin included in the data set is now y hat equals 2.29x plus 39.5. So you can see a big difference. Get my pointer up here. You can see a big difference between these two linear least squares regression lines. If we graph the two regression lines with Justin's data included in red, the bottom line, and without Justin in blue, we can see much more information about what the impact is with Justin's data. The inclusion of Justin Thomas's in the data set causes the slope of the regression line to decrease from 3.16 to 2.29, as we can see here, and the y-intercept to increase substantially from negative 55.8 to positive 39.5. Justin's data pulls the least squares regression line towards his data point. You can see that this new regression line now moves much more further towards closer to his point. Notice in the scatter diagram that Justin's shot has high leverage and a large residual based on predictions using the without Justin line. Therefore, Justin's data point is indeed influential. High residual, high leverage. As with outliers, influential observation should be removed only if there is justification to do so. When an influential observation occurs in a data set and its removal is not warranted, there are two courses of action. Collect some more data so that additional points near the influential observation are obtained, or use techniques that reduce the influence of the influential observation, such as transformation or a different method of estimation, for example, minimizing absolute deviation. FYI, these techniques are beyond the scope of this text and this course, but you do have some insight into it there.